This is my Eprom programmer. It's not a programmer. It checks Eproms. These are the old style Eproms. These are, I'm pretty sure you can see that. This is these are the 2764s, and they have this window that shows the actual die and the substrate inside there, which is the memory. And of course, these chips can be programmed, but then they can only be erased with ultraviolet light. So I have a bunch of these, and of course they were all erased, but I'm not sure. I wasn't sure if the cells were completely erased or if I might have missed some. So I built this to check them with. So what this basically does is you can see the LEDs, they're flashing here, and basically what these LEDs are indicating is that the EPROM is being addressed. Okay, because you can see here it's counting up in binary. I got a reset button on the Arduino. This is the Arduino Mega. All right, the 2560. So the reset button here. Let me reset it. It'll start over again, and you'll see that it'll start counting in binary. There you go. So now these EPROMs have 12 address lines, and so the total count for 12 address lines in binary would be 8,192. And that is basically an 8K byte address system. So this is an 8K byte, 8,000 byte EPROM, and individually that would have 65,536 cells. Okay, so that's quite a lot, isn't it? But anyways, this is scanning in byte form because it's accessing the address to cause the EPROM to output its data on these red lines, which are 8 bits, so that's 1 byte. But each one of these bits is being analyzed by the program. So even if inside the byte, even if there's one cell that's gone bad, it'll show you that. So now this is the actual circuit. It's very simple. The rest is just Arduino, and basically these are wired. The green lines are wired to the address lines of this EPROM, and they're also wired into the same location through the resistor and the LEDs. Because I needed a way to absolutely make sure that the address lines were being addressed. I mean, if I didn't have the LEDs, I couldn't be really sure if they were addressed or not. But since the LEDs are coming on, that tells me that there is a high signal and a low signal, turning them on and off. So that same signal is being applied to the EPROM. So that's just an indicator for that. This LED right here is actually connected to the output enable pin of the EPROM, and it stays low for the most part because the output enable and the chip enable on this EPROM are both active low. So when you have them low, that means that they're outputting data. I left it low all the time. All I'm doing is I'm just addressing the lines, and each time it's addressed, there's a slight delay in the program, and that'll cause the data output, the data output lines to output whatever data is on the cells. And once it's completed its entire cycle, in other words, all these lights are on, the program will end, and then this light right here will come on to turn the output enable on this chip back up to high, so it disables the output, okay? And that also tells you that the scan is complete. But the program itself will tell you that the scan is complete. So this is the actual circuit. It's very, very simple. And what I'm using here is I'm using the socket here is called a zero force insertion socket. So using that, it's easier to mount, I'm pretty sure a lot of you guys have seen this anyways. So now that's the actual board. So let me go to the program and I'll show you what I've done here, okay? So here we go. I'm just going to put this down here beside me. Now this is the actual program. I'm not sure if you can see that. Maybe I should zoom in just a little bit more. I think that's enough because I got to turn on the serial monitor. I'm not sure if the serial monitor will be visible. But anyways, okay, so this is the program. I'm only using this for the serial monitor, so I didn't need to include any libraries here. So basically, I just set all the parameters up here. I defined all the pins for the output datas in the LED pins. So that's straightforward. And then I set the variables to its beginning status, and then in the setup, I initialized the serial monitor, and I set the pin modes for all the outputs as outputs, and then the program starts. So this here, what you see here, this display binary function, is actually what causes the system to address the EPROM in binary, and it also is what is turning on the LEDs in binary as well. So this is the actual counter right here, and then the rest of it is just for displaying this on screen, what's happening. Okay, for example, this one here will tell you at what address it's accessing. The next one is, let me see here, the next one, okay, this one here is byte data. What this does is it concatenates or shifts all the datas, all the bits for each cell to the left, so that they concatenate in 1 byte form. And I call it byte data. So basically, it'll take D7, which is the most significant bit first, because that's shifted to the left seven bits, or seven places. And then the next one, D6, shifts over 6 places, so that bit will sit beside this one. And then the 5th one will sit beside this one, and the 4th one, and so on, all the way until it gets down to 0. So if the bits are all high, this will read 8 bits of ones, okay? Starting from the most significant bit to the least significant bit. And then the rest of it is, again, it'll print on the serial monitor what this data is in decimal form, which the number, when you have all bits of a byte are ones, the max number is 255. And so this will display that number, and then if the this part of the program here is basically detecting to see if you put any EPROM in the system. Okay, if the socket is empty, in other words, if there's no byte data being detected, it'll print no component is detected. So insert the EPROM if you want to test it. Pretty straightforward. Then this here will also take the byte data and display it as a hexadecimal notation. So for 8 bits, that'll be FF. So that'll display that. And now it'll display FF, obviously, if all the bits are ones. Okay, so if it displays anything other than ones, it'll give you what the hexadecimal number is for that. The next one will display the binary representation of the data output from the EPROM. And these are all in bit format, 8 bits long. Then this one here, this line will, if it detects that the byte data is less than 255 decimal notation, then the amount variable will increase by 1. So if the amount variable is higher than 0, or less than, if the byte data is less than 255 and the amount is higher than 0, then immediately the right beside that cell, it'll print this, that one part of, or all the cells in this byte, or maybe 1 or 2 or 3 or more of the cells in that particular byte is not erased. So it'll give you that immediate message, okay? And then obviously this is at the end of the program. So once the scan ends at 8,191 address locations, it will change the output enable LED to let me see here, yeah, right here, to high, and then it turns off all the LEDs that indicate the addresses. It'll turn them off, and then right here is the amount from this line up here. So if the amount is equal to 1, at least 1, okay, because it can be higher than 1, but if the amount is equal to at least 1, then the EPROM has been fully scanned. It gives you this message. It'll tell you the amount of bytes it has for an 8K byte PROM is the amount of bits is, like I said, 65,536, and then it'll tell you what the scan found. And the scan found that whatever amount has been recorded in this amount variable, it'll show that, and it'll tell you, obviously that's higher than 0, so that means that it found a problem. So it'll tell you that the scan found that this particular cell is not fully erased, and it's not okay to be programmed yet. So you have to try to re-erase it again to clear it up. Otherwise, if the amount is greater than 1, oh, I'm sorry, I got this reversed here. Yeah, if it's equal to 1, then there's something, is found a bad cell. But if it's greater than 1, then, oh my God, I'm getting confused here. Wait a minute. If it's equal to 1 itself, then yeah, it hasn't been erased and there's a bad cell. If it's greater than 1, the scan found that so many cells are not fully erased. Oh, the reason I did this is because you don't want to say that, it found that so many cells, plural with an S, are not erased if you only have one cell that's not erased. Okay, so I did this for proper English termination. That's it. I totally forgot about this. I apologize. But anyways, okay, so or else now, if the amount is greater than 1 or 1, it'll tell you it's not erased yet. But if the amount is 0, it'll say or else. If it's not these values, then it's scanned the EPROM. It found that all the cells are cleared and it's okay to be programmed. So there you go. Then it exits the program. So that's basically it. And so most of this is basically just for display, and the actual program is here where it sets up the byte data, and this loop here where it counts right here, display binary, where it counts it sets up the address for the binary counter, and then it also causes the EPROM to output data. Let me see here. It outputs data here, okay, and that which is recorded by the rest of the system, and it displays it all. So, okay. So, anyways, enough with this program. I'm going to turn on the serial monitor. Now, when I turn on the serial monitor, you'll see here that the LEDs will start over. So it'll be just by me clicking this up here. It'll reset this, and it'll show you everything I've been telling you. So here we go. Okay, so it has started over, and there's the serial monitor. Now, I'm not sure if you can see that. Maybe I should zoom in a little bit more. Just let me zoom in just a touch. Okay, there you go. Okay, now you can see here the first line is the address. It's showing the address in decimal form. And then these are the 12 address lines, which is increasing in binary. It's counting up in binary. The same thing as what the number is what's showing here in binary. Let me put it that way. And also, this is the LEDs that are flashing on this board is corresponding exactly to this counter. Okay, it's hard to tell because it's going pretty quick, but trust me, that's what it's doing. So then the rest of it is letting you know what the data output of the EPROM is. So 255 means that all the cells have been erased and they're all at a high value. In other words, see from the right side, it's showing the data output in binary format, they're all ones. Okay. In decimal form, all ones, 8 bits long, means 255, because that's the max that it counts to in 8 bits. In hexadecimal form, it's the letter R, FF. FF means that they're all erased, they're all high. The reason is because if you split these in four, groups of four, 4 bits long will count to 15, and the next 4 will count to 15, 0 to 15. But in digit format, there's no such thing as 2 numbers. So any number over 10 has to be represented by a letter. So 10 would be A, 11 B, 12 is C, 13 is D, 14 is E, and then 15 is F. So FF means all ones, all the way across. So now, as long as you see this, that means that the EPROM, it's detecting all these individual cells that have been erased, and it'll keep counting. The counter here will keep counting until it gets to the maximum of this EPROM, which in this case would be 8,191. And when it does that, it'll give you the result on the bottom. I'm just going to let this run and until we get to that point, and then you guys will see it, because it's going to take a couple of minutes here if you want to bear with me. And because once it starts getting up to 2,000 or 3,000, it goes pretty quick. So it won't take too long, and I'll show you what the result is. And then what I want to do after that is I want to try to scan again, but I'm going to purposely interrupt the scan to fool the system into thinking that there's the EPROM hasn't been erased, and I'll show you how it indicates on the serial monitor that there's a problem. Okay, so I'll do that after the scan is finished. So I'm just gonna let it run here, and you guys can either watch it or go get a coffee break or something and come back. But anyways, I'll leave it like that, and then I'll be back soon. Okay, thank you guys. Okay, I'm back, and the scan has been completed, and you can see what the message says here. The EPROM has been fully scanned. It has a total of 65,536 cells, which are 8K bytes, and the scan found that all the cells here are clear and they are erased, so it's okay to be programmed. Now, looking at the unit itself, you can now see that all the address lines have gone off, and that light has come on. Now that, like I said, it's indicating a high status because the output enable chip on the EPROM has been set to high. Like I said, both the chip enable and the output enable are active low on these chips, so they need to be high in order to disable it. So now what I'm going to do is I'm going to clear this serial monitor here, clear the output. Now I'm just going to scroll back here. Let me take the auto scroll off. I'm going to scroll back here, and you'll see that right beside all these ones, there are no other messages at all. Okay, none. They're all clear. And all of the data they're all ones, they're all decimal 255. So that indicates an absolutely clear erased EPROM, okay, ready to be programmed. Now, if there was a problem, there would be a message beside these ones that are saying, hey, this particular byte, there's something wrong with it, it's not erased. And it actually shows you in these numbers which cell in this byte array is not erased. So I'm going to do that on purpose because all of my EPROMs that I have checked them all, and they're all good. So in order for me to let you guys see what I'm talking about, I got to do it on purpose. So what I'm going to do is I'm going to clear this screen. Let me clear that. And I'm going to start the scan over here, but instead of running through the whole scanning procedure, I'm just going to do it very quickly here and then stop the scan, and I'll show you. Okay, now I've taken the auto scroll off, so I'm going to push the reset button on here to restart it. But then what I'm going to do is I'm going to lift this handle here for the 04 socket, and that will disconnect hopefully just a couple of the data output lines, and it should indicate that it's not detecting some output, and it'll tell me that there's a problem. It'll show up on the serial monitor. So let me try this and see what happens. So I'm going to start to scan. Okay, scanning. Now I'm just going to very quickly. I got to hold this kind of tight, but I'm just going to very quickly lift it. Let me put the auto scroll on so I could see what happens here. All right. So I'm going to very quickly lift it and then put it back. Oh, there it is. Okay, I got it. All right, now let me stop the auto scroll. I'll put this away. Now the scan is still continuing on this, but I'm not gonna wait till the end. I'm just gonna scroll back here to where I lifted up the handle. Okay, you can see here that the decimal data does not say 255, it's 224. The hexadecimal value is E0, 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 not FF. And they're all 224. As soon as that happens, as soon as it goes below that value, any value, even 254, it'll give you this message. It'll tell you that these cells have not been erased. But look at the way it shows you. You can see that it's 0, 0, 0, 0, 0, and then 1, 1, 1. So individually, it's telling you which cells are not erased. Like, for example, this would be in binary format. The number on the right side would be the least significant, and the left side would be most significant. So this tells me that the cells first, second, third, fourth, and fifth cells are not erased, and the rest of it are good. Okay, so anyways, yeah, that's how it works. And oh, you can't see the whole message. There you go, not erased. And that's how it works. And then at the end, when the program finishes the scan, right at the bottom, it'll give you a message. Well, you got so many of these cells that are bad, or so many of these bytes that are bad, and it's not okay to program it yet. Now, in my case, because the rest of the EPROM is checking okay, it would only tell me that there's 1, 2, 3, 4, 5, 6. So at the end of the scan, it will tell me 6 cells are bad, and then all you do is you scroll back up to see where the message is, and it'll tell you exactly at what address these cells are bad and how many of the cells are bad within the byte. So there you go, guys. Another one for your books. Oh, and by the way, one of my EPROMs was so bad it didn't even start to scan, and I was wondering why. I thought I had a bad connection, but as it turned out, it was because there was a blown B+ wire inside of the actual IC. Okay, so what I did was I broke the IC in half, where you could see the die on the substrate for the memory. This is the same thing. It's one of these EPROMs, and I opened it up and I checked with it under my microscope, and you could see that these little tiny gold wires in here. Where's my pointer? You can see that this is the substrate right here, where all the memory cells are, and these are the pins that come, the outside pins here, and there are gold wires that are connected from the die, the substrate, over to these pins, and they all go out to the corresponding pins. Well, in this case, there's a broken gold wire connecting to one of the pins here that feeds the, on this side, that feeds the supply pin right there. Okay, so this chip wasn't even powered. Now, I'm thinking the chip is itself is okay, but it's obviously it's unusable because you can't power it up. But I was just thinking, suppose there was a way of jumping that pin back to the substrate. I can get this thing working. That's just an idea. But anyways, I'm not going to bother with it. It's too much trouble. But let me see if I can focus in on this a little bit better. I don't know if you guys can catch that, but isn't that cool? This is the most awesome. Look at the technology, and this was old technology, like from the 70s and 80s. You can imagine today what it's like. Holy crap! Look at the size of this thing, and it's got 65,536 cells in it, but it's just unreal, you know. And by the way, this is done with a process called photolithography. And photolithography was first used when they started to make these things, and I think they're still using it. Photolithography. A photolithography is a process of reducing the image instead of expanding it, like in photography. And I guess they found a way to reduce it to almost atom size. And anyways, it's just unreal. Technology is really, you know, intriguing, isn't it? Anyways, guys, I'll leave it at that with that note, and I hope you liked the video. If you did, please give it a thumbs up, and also do not forget to subscribe so I can keep uploading these kind of things. If anybody has any questions or would like me to supply anything, just let me know in the comments, and I'll reply to you as soon as I can. All right. So with that being said, I hope everybody has a great day, and thanks for watching. Until next time, bye-bye.